Now to the Nobel Prize for Physics. John Clark, Michel Devoret and John Martinis have won the prestigious award. The US-based academics demonstrated how the bizarre properties of the quantum world can be made concrete on a human scale.
I'm Gavin Freeborn and this is Original Ideas, a podcast from the University of Liverpool. In every episode, we meet some brilliant people working in academic research, looking at the impact it has on our future, exploring the latest breakthroughs, and finding out the real-world impact research is having on society. In this episode, we shine the light on one of the most fascinating and fast-moving areas of modern science, quantum research.
We can replicate in our lab conditions that are experienced in very high vacuum, very cold, very sparse regions of the interstellar medium and of space with exceptional control.
Quantum is applied in electronics, including lasers in supermarket checkouts and car sensors, and this year is the year of quantum. We're moving towards using quantum technology for more complex feats such as supercomputers. At Liverpool, quantum is part of our particle physics research frontier, where scientists probe the smallest building blocks of matter, the fundamental forces that govern them, and technologies that help us study them. It's a particularly exciting moment in the centenary of quantum, and this year, the 2025 Nobel Prize in Physics was awarded for quantum breakthroughs, with experiments having implications for computing, sensing, and our understanding of the universe. To talk through this, I was joined in the studio by some brilliant quantum experts. Professor Brianna Heazlewood, who leads the Cold Chemical Physics Group, Dr. Jonathan Tinsley, whose work has contributed to international projects exploring gravitational waves and dark matter, and Marina Maneyro, a PhD student in our Innovation in Data Intensive Science programme. We discussed what the Nobel Prize and the Year of Quantum means for the field, how Liverpool is contributing to UK and global quantum initiatives, and what the future of quantum science brings for technology, fundamental physics, and society. So, Brianna, Jonathan, Marina, lovely to meet you and looking forward to talking through all things quantum. Firstly, Brianna, I know you use extreme cooling and precision techniques in your work to study how molecules and ions behave in quantum regimes. How would you explain to a non-scientist what happens when you cool atoms and molecules almost to absolute zero and make them collide?
Well, it's actually incredibly interesting and somewhat counterintuitive. So we use a method called laser cooling. It's this really elegant technique that was recognized in the 1997 Nobel Prize in Physics, and it's built on the principles of quantum mechanics. So the process relies on slightly detuning the frequency of a laser away from a resonant transition. That's an electronic transition inside an ion or an atom. And we do this so that the laser interacts only with the ions that are moving towards it. So we take advantage of something known as the Doppler effect. So these ions can then absorb and subsequently re-emit a photon. And a photon's a particle of light. So we repeat this interaction thousands of times, and we slow the ion down. And so overall, this results in a decrease in the velocity distribution of the ions, which corresponds to a lower temperature. So this is how we make them cold. So repeating this cycle again, thousands of times, results in ultra-cold ions, and we can observe these. We can watch them with an actual CCD camera and a microscope because we can observe their fluorescence, that is the photons that these ions emit as part of their cooling cycle. So they're constantly absorbing these photons and then emitting them. And so we collect the emitted photons as fluorescence, as light, and we image them with a camera. And the coolest thing about this, they're cool anyway, literally, but the really cool thing for the science is that we can see them. We can see these ions react in real time, and we can see the rearrangement of what we call a Coulomb crystal, the positions of these ions, by tracking the movement, by monitoring their fluorescence as a function of time. So to complement this direct imaging, we've also devised a method for quantitatively identifying all of the trapped ions. So the challenge is that we can only laser cool a certain subset of species that have these really nice closed transitions. If we want to look at anything else, they're effectively dark to us. So we've come up with other methods for studying these dark ions so we can see what they're getting up to as well. And so we use different fields. We use electromagnetic fields to move our ions into a flight tube, and we perform what we call time-of-flight mass spectrometry measurements. And so this gives us quantitative details, including the mass and the relative abundance of all of the species that we had in our trap at a given reaction time. So it gets rid of any assumptions we have to make about the non-laser cooled ions, and it lets us study complex reaction systems. And the reason we want to study these complex reaction systems is to really understand fundamental questions across science. So we really want to use the quantum properties of these species and these techniques to understand, for example, how the universe formed. So the relative abundance of hydrogen and deuterium. So deuterium is heavy hydrogen. It's hydrogen with a neutron. It can reveal key information about the conditions of the early universe. So the evolution of stars, of planets, the origin of water on Earth even. And so to really understand these processes and how this happened, we need to control the experimental conditions. And we do that by using all of these quantum techniques. So we've observed, for example, something called a kinetic isotope effect, an inverse kinetic isotope effect. We've found that deuterated ammonia reacts faster than hydrogenated ammonia. And we found that is super interesting because about 10% of hydrogen-containing molecules in interstellar space are known to be deuterated. 10%. And that's in spite there being more than 100,000 hydrogen atoms for every deuterium atom in a cosmic environment. So that's crazy, right? There's this big mismatch. This is a really key open question in astronomical science. Why is that? We still don't know. But using these quantum techniques, using the quantum nature of the particles that we're studying, are providing new insights into this process.
Absolutely fascinating. Now, Jonathan, touching on some of your work, what does it mean to launch ultra-cold atoms in a 100-metre fountain, and what does measuring the interference of these atoms tell us about dark matter or gravitational waves?
So I think to answer that question, we have to start with the second part and understand what it is that we're trying to do and how it works and why. So this really goes to the kind of heart of quantum physics. So in particular, we have atoms, which are matter, and we have an atom interferometer. You said this measures interference. Now, interference is really a wave phenomena, whereas you think of atoms as like particles. Normally, we think of them as kind of little objects that bounce and collide. Here we'll be bringing them together and making them behave like waves. So how is this possible? Well, it really is due to a fact that in quantum mechanics, everything is both neither a wave nor a particle. Sometimes behaves like one, sometimes like the other, but it is in reality some kind of quantum object we don't really understand. And this is known as wave-particle duality. And it really goes back to the very foundations and heart of quantum mechanics. So Albert Einstein's Nobel Prize actually was awarded for understanding that light has this particle phenomenon. So we normally think of light as being like a wave, but he was able to show it really actually behaves like a particle. And a bit later, Louis de Broglie extended this not just to light, but doing the reverse, to say actually matter, things that we're all made up of. So atoms, all electrons, everything like this, fundamental particles actually also have wave properties. So what we do is we exploit these wave properties of the atoms. Now to do this, we have to get at the kind of quantum level, because obviously we don't see this in real life. You don't behave like a wave, I don't behave like a wave. If we ran into each other, we wouldn't interfere, we'd collide, it would hurt a lot, right? So instead, what we have to do is use exactly the techniques Brianna was discussing to make them ultra cold. And the issue we have though, when they get ultra cold, is we've taken out all of the energy and now they fall. So they fall under gravity. Atoms also have mass. So we want to experiment with them for a long time. The longer we have them, the longer we can interact with them, play with them, the more sensitive, the more information we're going to get. So to do this, we're building larger and larger devices, interferometers, which is, as you said, one in particular is MAGIS, which is a new experiment, a US-UK collaboration that's being built at Fermilab, it's a national laboratory for particle physics and accelerator physics in the US. And there we have a 100-meter tube. And again, one option is to just drop the atoms. So if we drop the atoms, then they fall 100 meters. But even better is to launch them. So if we launch them from one position up, they will go all the way up and come all the way down. And we'll get twice the amount of time. And this is an atomic fountain. Now, the beauty of atom interferometry is that you split these atoms into spatial superpositions. Now, what do I mean by this? I mean that the atom is simultaneously in two places at once. And the larger and larger we can make this separation, the more sensitive we get. Why? Because basically anything that interacts with the two arms, so the two different positions of the atom, differently, we'll be able to measure when we bring the atoms back together and measure the interference pattern. So in particular, you mentioned about dark matter. The idea is that dark matter is something that pervades the universe, is actually way more abundant than normal matter, but we can't see with telescopes. So it doesn't interact with light in any way. It only interacts gravitationally, and therefore we call it dark. So we can measure the gravitational mass of this, but we can't see it or understand what it is. It doesn't fit into the standard model of particle physics. And one idea is it's this form of not really matter, again, coming back to wave-particle duality. It's really like a wave that's kind of pervading the universe or pervading our galaxy. And as this wave comes through, it interacts with our atom and causes its energy levels to oscillate at the same frequency as our wave. And we'd be able to pick up that signal by looking for oscillating interference signal in our device. And the other example you gave, which is really exciting, is gravitational wave detection. So a gravitational wave is caused by from Einstein's general theory of relativity, space-time itself is like a kind of sheet or body that has kind of dynamic behavior. So a kind of gravitational force is replaced actually by the curvature of space-time. And the idea is not only can it curve in DC, but you can kind of make it wobble. You can make it move, and these kind of events are gravitational waves. And what's exciting about gravitational waves is it's like light waves. We can look and see all the skies and the stars. This is a whole new way, if we can detect them, of looking at the universe. So we can look back in time, we can see black hole mergers, we can see beyond even further back in time than we can see with light, to the very furthest reaches of the galaxies. And the idea is, again, here, we have atoms that are freely falling under gravity. The gravitational wave, when it comes through our device, it stretches space back and forth with the wave. And we'll again see this as an oscillating signal as the wave comes through. And this is kind of a really exciting goal. We'll be able to bridge the gap between light-based interferometers that are currently used for measuring gravitational waves. They look at one particular frequency. We're going to look at a different one. So this is analogous to having, say, infrared telescopes or radio waves and light waves. They're all electromagnetic waves, but they're all different frequencies. You need different devices to see different ones. We're the same. With gravitational waves of a spectrum, we're going to look at a different part of the spectrum, which allows us to see whole new astrophysical events. To do this, we're actually going to have to go even more than 100 meters. We're going to actually have to make this thing a kilometer, probably, or put them into space where we get even more time to play with these things.
Amazing. Absolutely amazing. Thank you, Jonathan. Now, Marina, your PhD combines quantum computing with particle physics. How does a quantum computer differ from a classical one when it comes to simulating particle collisions or neutrino interactions?
Well, it's probably a good idea to start with what a quantum computer actually does and how it differs from a classical computer. So you may be familiar with classical computing, where we're working with bits that can have values of 0 or 1. In a quantum computer, what we're using is the very fundamental small-scale properties of matter, the quantum properties of matter, to also perform calculations. And instead of a bit, then we're using an element called a qubit, which shows this quantum properties. So instead of having a state of 0 or 1, we say that it's in a combination of those states, which is what we call superposition in quantum mechanics. And what this superposition allows us to do is essentially work on both of those states kind of at the same time as we compute using this qubit. The number of actual states that we can work with grows really fast as we introduce more qubits to our computer. So a quantum computer is very well suited to working with problems where we have a large combination of possible answers, because we can represent all of them using these qubits. So in the case of particle physics, there's a natural affinity with quantum computing, because we're trying to look at the very fundamental components of our universe and trying to understand how it came to be the way it is, right? And at this level, the particles that we're studying are also quantum. And that means that at times performing simulations to understand what these particles are doing is really difficult in a classical computer, because, well, we have to keep track of a really complex system. And so it may be that it takes a really, really long time to do this on a classical computer. It may be that we just can't perform the calculation at all. So the question I'm trying to answer is, for the case of neutrino interactions, can we actually perform any implementation of a calculation in a quantum computer that will help us get better results than we can get in a classical computer at present? So in neutrino physics is quite elusive in a way, because neutrinos are particles are everywhere around us, but they don't really interact very much with other particles. So when we're performing an experiment to understand what these neutrinos are doing and how they're behaving, usually we're looking at an interaction with an atom, because that way we can maximize the chances that we're actually going to see anything happen, an interaction happen. And the problem with that is that then we need to understand what's happening within our atom when we perform any computational models to understand what our experiment is saying or to design our experiment. So what I'm looking at is how we can model the nuclei of the atoms. And this is a very delicate problem, because we need to look at all the interactions between the protons and the neutrons that make up the nuclei. And, well, the bigger the nuclei in terms of like the amount of particles that it contains, the harder it's going to be to calculate, essentially. So that's where we hope a quantum computer could help us get more sophisticated results and increase the precision, which is necessary as we become capable of performing bigger and better experiments, which give us much more accurate results.
Amazing. Thank you very much, Marina. So I know that we get a lot of people listening to this podcast who are policymakers, industry stakeholders, and prospective students interested in innovation. Why should we all care about research in quantum sensing, cold chemistry, and data-driven science? Can each of you share a brief story or example of a potential real-world impact of your work? Brianna, we'll start with you.
If I start with the big picture as to why people should care, just in a general sense in the first instance, I think government and commercial investment in quantum tech is now approaching the £100 billion level. And we've seen amazing advancements with what's now called quantum 2.0 since the 1980s. And so quantum properties such as entanglement, the properties John explained so beautifully in the experiments he's doing, they're really being used as a resource for new technology. So we're seeing applications in a range of fields that are taking advantage of these quantum properties. I would say that much of what our research group does here in Liverpool is very fundamental. What we're trying to answer are very fundamental questions, largely about chemical reactivity, that are still unanswered despite having been of interest and being looked into for decades, if not longer. But some of the advancements that we are seeing is actually in the technology, in the sensors, because we have to detect things so precisely. We have to be really able to discriminate tiny signals from background noise. And so that level of precision and that level of detection sensitivity that we need for our experiments can also benefit just more broadly technological advancements. And so we're seeing things that we need to do our experiments being adopted by industry, for example, in how they produce sensors, how they produce different drivers for bits of commercial kit that we needed specifically for our work, but that then benefits industry more broadly. And so you really have that nice connect between seeing things in your lab go out and become pieces of commercial kit that someone else could buy for some totally different application. But that fundamental science is what drove that innovation. And so it's really nice to see that connection between the real at the forefront of knowledge in the lab, doing things people haven't done before, seeing things people haven't seen, and then see that link happen some years later with, oh, you can now buy this driver for this radio frequency field that we happen to need that actually can benefit other people in a range of other disciplines. So it's really interesting seeing that. I don't know if you've got other examples from your work, John, where you've seen some go from the lab to the real world, if you will.
Yeah, absolutely. I mean, so all sensors, as I mentioned, for example, are extremely sensitive to anything that's acting on the atoms. So this means they're really general purpose. We're principally often looking for fundamental physics, at testing quantum mechanics, looking for dark matter, looking for gravitational waves. But actually it's sensitive to a whole class of things. So electric fields, magnetic fields, and in particular, it's sensitive to gravity. So there's no way to shield from gravity. So in general, you can shield from magnets, you can shield from electric fields, but there's no anti-gravity. There's only positive mass. These can only attract things. There's no repulsion from gravity. And what this means actually is that our sensor, no matter what we do, more or less, will be sensitive to these things. And that actually has a huge number of real-world applications. Just to give a few examples, since Brianna's mentioning some numbers, I believe the most recent government figures for roadworks and civil engineering costs that are necessary is around £9 billion a year. And this is because essentially we don't know what's underground. So when you dig up, you see the roadworks, you see half the roads dug up and they're just dealing with one tiny pipe. And you're like, why is this? It's because we don't know where the pipe is exactly. Now, one way you could get around this would be to use an atom interferometer, a portable one, and take this and scan. Why would that work? It's because the pipe has slightly less mass than the surrounding ground. So you see a slight reduction in your gravity sensor. And this actually allows you to map this road, the space, whatever it is you want to do the engineering before you, say, dig up the road and cause weeks of roadworks when you only need to do a tiny little bit. This is just one example, actually. They're being used for archaeology, for monitoring water levels is a very recent one that people have got interested in. Looking for seismic monitoring, so earthquake prediction, volcanic activity prediction, carbon storage. So we all know there's these carbon capture ideas where you store your carbon underground to keep it out of the atmosphere to help with climate change. But is it really working? Is it leaking? All these kind of things. Again, you can see that mass moving because our devices, they're so sensitive, they can tell if you're near or you're far of this mass in the pipe, but it's not. So how do we go from kind of what we're doing, it's 100-meter scale, etc., and bring that to the real world? So there are some commercial companies doing this. We in Liverpool, we're looking to translate our kind of state-of-the-art detection systems and platforms that we're developing for these experiments and thinking about how can we make them more amenable for industry, so more transportable, more robust, developing smaller, colder versions of what we're doing. These are all things we're interested in that would then feed in to this kind of burgeoning quantum sensors environment.
Excellent. And Marina?
Yeah, so in my case, I also work with quite a fundamental problem, but the beauty of the quantum computers and the algorithms that we use is that they're not just for one purpose. They can be used for different types of problems. So the most direct connection, perhaps, in terms of what I'm working on, is that the algorithms that I use are really similar to what's used in a very promising field of application of quantum computing, which is quantum chemistry. So from this field, instead of looking at, for example, nuclei, they look at stuff like molecules and how molecules behave. And this can be really helpful in a lot of applications, such as developing drugs. But again, the quantum computers could also be used for many different areas, such as optimizing logistics or even finance and stuff like that. It doesn't need to be specifically a scientific application.
Maybe if I add also, just to come back to what Brianna was saying about Quantum 2.0, is I think what a lot of people don't appreciate necessarily is how much quantum mechanics and its technologies is already part of our everyday lives. So the Quantum 1.0, as it's called, this gave us lasers. This is on every checkout at every supermarket. It's in your things like semiconductor technology, which of course underpins all of our electronics. This all came from the original explosion of quantum mechanics. And what we're seeing now is hopefully something comparable, but on a larger and more kind of complex scale, really using these more sophisticated parts of quantum behavior like entanglement, which is really what allows Marina and other researchers to utilize the full power of quantum mechanics. And I think this is really just the first stage, that these will be powerful devices getting more and more common and more integrated into everybody's life.
To pick up on that as well, the Quantum 2.0 and something we haven't mentioned so far is really being picked up in medical applications. So the government has a big push to try to get quantum into the NHS by 2030, which is ambitious, but already there in many respects, actually. So they want to do more, but already a lot of the techniques that have come out of the experiments and the work very broadly that each of us are connected with sees this really sensitive detection of, for example, magnetic fields. And that's being used already in sensors for detecting biomagnetic fields, so neural detectors, modeling what's happening in the brain. So using these really sensitive atoms, these methods that have come about in a lab with isolated particles and scaling them up and using those techniques that allow us to really precisely map what is happening, where it's happening, and applying that to, say, the human brain. And so there's really interesting applications that are coming out of Quantum 2.0, and that's only going to increase as we see more and more breakthroughs and we get better at understanding how it's happening, why it's happening, and scaling it up.
And there's actually even a bit of a two-way street. So it's going back a bit, but one of the NMR machine, this is really based on actually also quantum properties, quantum interference of nuclear magnetic moments. And a lot of what we're doing for fundamental physics at the minute is going back and looking at what they've already done and realizing how can we use the same techniques for our sensors, for our whatever. So there's a nice kind of actually circular synergy and positive feedback loop at the minute, I think.
It's incredible to think that when someone comes from Royal Mail, for example, to pick up a parcel and they've got their scanner in their hand, that there's quantum mechanics involved there when they take their parcel from my house for a return, or et cetera, et cetera. As far as the other connection to one of our recent podcasts around neuroscience and pain, and obviously a lot of the experiments that they may be doing around neural networks involving quantum computing, and another podcast that we also did was around therapeutics innovation, but they may also be using quantum as well.
Quantum's everywhere.
Quantum is everywhere, exactly. It's unquantifiable and quantifiable at the same time. So one thing we talk a lot about here in Liverpool is quantum education and training, offering students opportunities to learn about quantum science and get involved in quantum research. For people interested in knowing more, what collaborations are happening at Liverpool? I'm thinking of partners such as CERN to tie in with the particle physics research frontier.
I think there's a lot. So as you see, my research and research we're doing on atom interferometry, we're really looking at dark matter detection, which is fundamentally a particle physics question as well as an astrophysics question. Marina, of course, is how to use these techniques to answer really a pure particle physics question to do with neutrinos. And I think that's actually something we're seeing a lot at the minute. Is a really nice synergy between what particle physics is doing and what quantum technology is doing. So to give an example, there was a lot of quantum technology push from CERN and also from the UK previously about how to use this for fundamental physics, how to take these advances and we want to use them for medical imaging and for looking for pipes and things like this. But we also want to say, well, can we use this to advance science? So the next frontier of particle physics might be how to be more precise, better measurements. That's how we're going to get to the next level of understanding. And to do this, we're going to need to really exploit the exquisite sensitivity you get from quantum sensors. So there's that going in. But equally, we have the other way around. So we have the quantum technologies. To really get the most of them, we said we have to make them really large. So I said MAGIS is 100 meters. Maybe we want to go to a kilometer later. This is not something we can do here alone at Liverpool. We have a 1 meter device. It's already very nice, but 100 meters, that's the size of the LIVA building. We can't do this alone. So this is where you start to get a particle physics style impact coming into quantum research, which is large collaborations, sharing of knowledge, really working together to maximize our resources to get the best possible result, and really focusing this on fundamental physics. So this is a big drive we're seeing. So that MAGIS we're doing at Fermilab, and we also have AOM, which is a UK-wide collaboration. So several universities and research institutes in the UK coming together to try to build a 100-meter device. And additionally, we also have initiatives that we're involved with at Liverpool that are hosted by CERN. So in particular, there's an idea for a terrestrial very long baseline atom interferometer. So this is looking forward to that kilometer scale, how to measure gravitational waves. This is being hosted by CERN. There's a collaboration we're part of for this, doing design studies. And also there's a plan very recently, only the past month or so, it's been put out to build an atom interferometer potentially at CERN. So a 100-meter device at CERN. And there's also technology transfer, a quantum technology platform at CERN called DRD5 that we're involved in and working on for several levels. Maybe Brianna can say something about that.
Yeah, so that DRD5 is the Quantum Sensor Research and Development Project for Particle Physics. So that's a collaboration that brings over 100 institutes working on quantum sensors for particle physics together. And Liverpool is one of these key members. And so we really are, as you say, really connected at an international level, as well as a national level, as well as even just different groups, different departments within the university working on so many different quantum-related questions. It really is fantastic seeing the scale of the collaboration and the different types of questions that are being tackled with all of these quantum-related research ideas. I think quantum education is just incredibly important on multiple different levels. There's a really high demand from the quantum industry for skilled graduates that have hands-on experience and a strong knowledge of quantum science. We've already mentioned the kind of the scale, the size of the quantum industry at an industry and a government involvement throughout that. And there really is this need for trained scientists to enter this space. There's a demand. They are in demand. There's also a need for people across a wide range of professions to be what's called quantum conversant. Physics teachers, for example, need to know enough to be able to teach their students. And we've spoken about how quantum really is pervasive, it's everywhere. And so even increasingly, members of the general public are aware, and there's a need for a general knowledge about quantum science, what it means, how it's used, where it's going. And so we really need to focus on skills training. So for the next generation and for the future workforce. And so we're working on that in a number of ways. We're trying to come up with ways of connecting teachers with the research and with the newer outputs and updating them, informing them so they can train their students, but then also teaching the undergraduates here. So John's teaching a core fourth year module, for example, that I'll let you speak about rather than me describe it.
Yes, so I teach the year 4, so it's our master's level advanced quantum physics. And I think what Brianna says is exactly correct. It's this is really having a lot of investment, but not just investment, growth in investments. Every year it's more, and every year it's from all over the world this is happening. So we need to be producing more and more people. It's not like we produce one set and then it's done. This is really a growth area. So we're always focusing on how to get these skills across. And then this particular advanced quantum course, one thing is involved is trying to keep it up to date. So every year we make sure, or I make sure, that we have not just the real classics that people need to know to an advanced level, but what is the more recent advances. So for example, just last week, I did a lecture on quantum computing, and the week before we talked about quantum simulation and things like this, and making sure really our research that we're doing that's really at the state of the art, some of that knowledge is getting given to the students, partially so they can understand and then contribute. But even as Brianna says, even if they go into a completely different field, it's about making sure they're aware of this, so they're quantum conversant. So you mentioned AI a little bit before. I think this is something that everyone's now aware of AI and has to be a little bit conversant. But I think it's going to be the same with quantum. So quantum, we said, is going to get more and more involved in our lives, play a bigger and bigger role, potentially, hopefully. And it's going to be equally important that people know what it is, how it works, even at a general level, so they can understand the technologies, what's going to work. It's going to be important for business. It's going to be important for politics, international relations.
And giving them those opportunities to gain those hands-on skills.
Yeah, of course. So, example, I know Brianna in her lab is always hosting students. We're always hosting students in our Atom to Fromtu lab. For example, even this year, I have a student working with us on his BSc, and he specifically wanted to do a project which he thought would help him get into this quantum industry. So we've kind of designed what he's doing to really give him a broad range of skills. So instead of saying, here's a niche physics problem for you to crack, we're giving him a little project where he's kind of building something. So he's going to learn the full set of skills you would need to really enhance his CV, and also to really make sure when he gets to that workforce, he's going to be really an asset and useful.
Excellent. Yeah, every day is a school day, and we are all about learning. So it's been wonderful to meet you all and to interview you and to be enlightened about quantum. So I will look forward to continuing to watch your careers and hear about what we learn going forward.
Thanks so much for the opportunity. It's been loads of fun.
Thank you.
Thank you.
You've been listening to Original Ideas from the University of Liverpool, and a really fascinating episode looking at quantum science and research. Thanks as ever to my guests, Professor Brianna Heazlewood, Dr. Jonathan Tinsley and Marina Maneyro, for taking time to give us some insights into their work. If you've enjoyed listening, please do check out some of our other episodes from the series. We've looked at topics such as clean air.
It might seem perfectly fine to you, but you're constantly breathing these particulates in.
The future of AI.
We really see the AI tools working side by side with the humans who are going to be deploying them.
And even our relationship with food.
When children and adolescents see food marketing, it can influence a whole hierarchy of knock-on behaviours and effects.
Head to liverpool.ac.uk/research, where you can also sign up to our monthly research newsletter with updates on events, opportunities to work with us, and much more. Thanks for listening. See you again soon.